Yeah, looking forward to talking about machine translation and sequence models today. As always, I'll welcome discussion on this. Some of this this is kind of the basic modeling stuff regarding machine translation. So I think some of this might be elementary for people who have taken an NLP class before, but there are, some people who might not have covered this. So I'd like to go through it. After this, we're going to be talking about some concrete code details. So looking at code from the Annotated Transformer and also from the assignment. And as always, please feel free to ask questions on chat or like live anytime you want. So language models are basically generative models of text. And what they do is they calculate the probability of a text X given, calculate a probability of a text X, and they allow you to sample from this probability distribution to generate outputs with a high probability. And so given this, if we train on a particular variety of text, like let's say we train on Harry Potter books, the sampling distribution will generate things that look like Harry Potter. There's also conditional language models. And conditional language models don't just generate text, but they generate text according to some specifications. So if we have our input X, and our output Y, our input X could be structured data, output Y could be a natural language description. What we're going to talk about this time is translation. So input X could be English, output Y could be Japanese. Our input X could be a document, output Y could be a short description. And our input could be an utterance, output a response, input image, output text, input speech, output transcript. So you can see that a lot of things, a lot of different tasks, data to text generation or natural language generation, translation, summarization, response generation, image captioning, and speech recognition all fit within this general paradigm. So because of this, these are a very powerful and widely used variety of models. And so I'd like to go a little bit into exactly how we formulate this problem and learn these probabilistic models. So when we calculate the probability of a sentence, the way we can do that is by taking a sentence which consists of I words and calculating the probability by the product of the probabilities of the word in the sentence. So if the next word is xi, we calculate the probability of xi given all of the previous words in the sentence. And this is a particular variety of language model. Oh, sorry, there's a language in 10, sorry. I'll find a good place to cut off this description and switch over to the language in 10. I'm totally slipped my mind. So then condition language models, basically what they do is they condition on some added context and they calculate the probability of Y given X. And then they do the same thing where you condition on X and all of the previous generated words. I talked about calculating the probability of words in a sentence, and in most cases, we're taking the previous context, calculating the probability of the next word given the previous context. These are also called by a variety of names. One name is an autoregressive link model, where basically that means we're predicting the next word given the previous words in some order. Specifically, when the words that you're predicting the word here from all come to the left, they're also called left to right language models. And there's also a term causal language models, which I don't prefer as much, but you'll also see in the literature. And basically, if you have a left to right language model, we can use something like a recurrent neural network to feed in the previous word, predict the next word, feed in the previous word, predict the next word, feed in the previous word, predict the next word, et cetera, et cetera. And if we want to develop a conditional language model that conditions on some sort of context to predict the probability of the words, the upcoming words, we can do something like feed in the conditioning context into a recurrent neural network and predict the outputs like this. So basically, we read the conditioning context one by one. Maybe it's a Japanese sentence, and then we predict the probability of the output, the English sentence one by one. So we have the encoder, so this is often called an encoder, and this is called the decoder. So these are often called encoder-decoder models. And they're used pretty widely in all of NLP nowadays. So I'll actually skip that part. So now we have this model, we can train it. I think a lot of people, or everybody in the class, is now training models for part of speech tagging now. So because of that, I assume like about the recurrent neural networks and other things like this. The place where these kind of sequence models or translation models become different is that we need to do generation from the models. And so instead of like taking in individual words and trying to put a tag on them, we actually need to generate outputs. And the generation problem is basically we form a model of P of y given x, and how do we use it to generate a sentence? And there's basically two methods. The first method is sampling, where we try to generate a random sentence according to the probability distribution. And the next method is argmax, where we try to generate a sentence with the highest probability. And in general, in translation, which is the main topic of this lecture here, we use the argmax. And actually, maybe I'll explain why in a few slides after I explain each method. So for sampling, the most common way to do this is called ancestral sampling, where we randomly generate words one by one. And the algorithm for doing so looks a little bit like this. So we have while yj minus 1 is not equal to the end of sentence symbol. So basically, while we have not yet finished our sentence, we calculate the probability of the next word given all of the previous words in the conditioning context, and we randomly sample a word from the next time step. And this is a method for an exact method for sampling from P of y given x. So this will give you, basically samples that exactly follow the probability distribution that the model specifies. If you had a really, really good model where basically it only assigned probability to y that were, plausible translations for x, then probably this sampling would be fine. You would get different translations every time, but each translation that you sampled would be good. However, unfortunately, our models are not all that great. And very often, if you sample kind of lower probability things according to this probability distribution, they might not be very good translations. So what we try to do instead is do some sort of search for the highest probability translation. And one way to do this is doing something like greedy search. So basically, one by one, we pick the single highest probability word in the output. So that looks a little bit like this. We similarly, we go until we reach the end of sentence symbol. But instead of sampling a random word according to the probability distribution each time, we take the highest probability word at the next time step each time. So what this is doing is this is, instead of picking, any old word next time, it always picks the highest one, which moves us closer to a very, high scoring output. Unfortunately, this is also not exact, and it causes real problems. So for example, it will often kind of, regardless of what the syntax should look like, it might try to generate the kind of easier words in the sentence first, because the easier words in the sentence will have higher probabilities. So this argmax, this greedy argmax, will try to choose those words first. And another issue that this can bring up is it will prefer multiple common words to one rare word. So like, for example, if we had a choice between New York and Pittsburgh, even if the product of New and York was lower than the probability of Pittsburgh, if the probability of New only was higher than Pittsburgh, this greedy search would kind of make that decision prematurely and not be able to back off and reconsider the decision later. So what we do instead is we have a method called beam search. Yeah, there are other methods as well, but beam search is the most common method, where instead of picking one high probability word at every time step, we maintain several paths. So this is an example of beam search with size 2, where basically we, instead of like taking the highest probability word at the first time step, which would be B, we consider 2 high probability words at the first time step, A and B. We expand all next words for each of those possibilities, and then select the highest scoring sequence of length 2 based on all of these. And basically, beam search allows you to spend more time computing to look for a high scoring output, and basically allows you to do more precise search and help resolve some of the issues that I talked about on the previous slide. Cool. There's also lots of other details if you want to go deep into the details of this. For example, there are other methods for sampling that try to kind of alleviate the issues that you get from low probability outputs by only sampling from the highest probability outputs, things like top K sampling and nucleus sampling. There's also other methods for search that incorporate, like dynamic beam sizes or other things like this. But basically these standard beam, in machine translation, standard beam search tends to be the thing that most people use, and you usually just pick a beam size of 5 and forget about it and hope that that's good enough, and it usually is. Cool. Any questions about that before I move on? Okay, guess not. So actually, sorry, I need to check chat too. So next, I'd like to talk about attention. So attention is very, very important in machine translation. And one issue with the example like machine translation model that I talked about before is basically what we're asking this model to do here is read in a whole sentence, express all of the meaning in that sentence in a single vector, and then output the appropriate translation based on this. And because I have previously worked as a translator, I like to make an analog to what that would be like if you were asking a translator to do something. So this is kind of like asking a translator to read a whole sentence, memorize that whole sentence, put the book that they were looking at away, and then try to translate, output the whole sentence based entirely on their memory. And for a lot of sentences, a lot of things that people think of, they might be able to do that, but it's a lot harder than if you can go back and reference the like original sentence when you're doing translation. And so this was kind of eloquently stated by Ray Mooney, a professor at UT Austin, where he said you can't cram the meaning of a whole bleeping sentence into a single bleeping vector. And so the idea of attention is basically to relax this constraint of memorizing all of the content of a sentence in a single vector and put it into multiple vectors, one vector for each token in the input. So then we have the model that goes back and references each of these vectors one at a time. So the basic idea behind attention is that we encode each word in the sentence into a single vector. And when decoding, we kind of perform a linear combination of these vectors weighted by attention weights. And we use this combination from the vectors in picking the next word. And I have a graphical example of this here. So let's say we have our encoder here, and our encoder calculates a representation for each word in the sentence. And our decoder here basically is stepping through the sentence word by word. And it's gotten to the place where it's at like, I hate, and that it wants to generate the next word. So what a translator would do at this point is they would go back and reference the original sentence, maybe after they've read through it once, and try to decide which word they want to be translating next. Think about what word they want to translate that into. And that's basically what attention does. So it takes this query vector down here, and it compares that query vector to all of the key vectors in the original encoded input. And it calculates a score or a weight based on the congruence between the query vectors and the key vectors. So you put it through this function here that takes in the query vector and the key vector, and it spits out a scalar weight. And we do this for each pair of the query vector and one of the key vectors in the key matrix, basically. And then we normalize these, so they add to 1 using a softmax function. And basically what this looks like is we take in these values and we output something that looks like a probability vector here. And I'm sure everybody's familiar with the softmax from the homework that you're already working on. Then after we do this, we take the value vectors, which are the things that we want to attend to, the types of information that we want to combine. And we multiply this by the attention vector here. And that gives us a single vector that we can then feed into any part of the model. And specifically in the case of machine translation or whatever else, we will be feeding this into the decoder in order to calculate the probability over the next word. So if we have a attention mechanism when we're doing translation, this is a picture from the paper that introduced the attention mechanism. Basically, you'll see that every time it translates a next word, I believe in French here, from English to French, it will be attending to multiple words in the original source document. So, and you can see that these align with each other, and even when like the order reverses, then the appropriate words are being attended to. So I left the actual function that we use to take in the query and the key vector underspecified. But if we assume that the query and the key, Q is the query and K is the key, we can do various things like feeding the query and the key into a multi-layer perceptron where we concatenate them together, multiply them by a weight matrix, take a nonlinearity like the tan H and multiply by another vector to get this value. This is flexible and often very good with larger data sizes. Another thing that we can do, and in fact, this is maybe the most common method that we use nowadays, we can multiply by the key we can have the key and the query, and we have a weight matrix here that we multiply. And this gives us the attention weight here. And then we also have other things like the dot product, where we just take the dot product between the two vectors. This is very, very simple and can be effective, but the problem is that this one issue with this is this definitely requires the key and the query to be the same size, because otherwise you can't take the dot product. So the bilinear function gives you a bit more flexibility in that you don't have to assume that the query and the key are in the same kind of like underlying space, and it also allows you to compare things of different size. And then finally, we can have the scaled dot product. And so one problem is that the scale of the dot product increases as the number of dimensions gets larger. And so the way of fixing this is basically scaling it by the size of the vectors. So you take the square root of the size of either the key vector or the query vector. It doesn't really matter which one, because they're both the same size here. And this allows you to make sure that even if you have larger or smaller values, the scale with which the attention weights varies stays approximately the same. Okay, so this is a brief overview. We'll be going through some concrete examples a bit later in the class, but are there any questions here? I imagine many people will be familiar with this already. Okay, if not, I will go ahead. So then we have improvements to attention. So attention, one issue with attention is basically that neural models often tend to drop or repeat content when they're doing generation. In particular for tasks like machine translation, where in machine translation, we can make the implicit assumption that all content in the source should be translated into the target. We can additionally add biases to that basically model how many times words in the input have been covered. And if they have not been covered, approximately one time, we can give some sort of penalty. So basically, this is making the assumption that each word should be translated about once. Or another option is to let the model, to tell the model how many times each word has been covered, but let it learn to use that information appropriately in making its next translation decisions. So either way, this is explicitly or implicitly encouraging the model to, cover things once and only once, or like as many times as necessary. Another very common improvement used in most models nowadays is multi-head attention, where the idea is that we have multiple attention heads that focus on different parts of the sentence. So this is an example where essentially what we do, this is an example with two attention heads, and the two attention heads each have a different function. The first attention head is like a normal attention head that is just used to calculate representations of the words in the sentence. So kind of like how I explained attention before, as a way to combine together information at each time step. And then the second attention head is basically focusing on words that should be copied from the source to the target. And this is used in particular for a summarization task where lots of copying needs to be done. So basically it's summarizing source code into function names. So what you can see is the first attention head, because it's just pulling in information about the input sentence in general, it's kind of spread out across the entire input sentence. And the second one, because it's kind of choosing which words to copy to generate outputs, is very focused on individual words, as opposed to being spread out across the whole sentence. And so I like this example because it gives an example about how, like, theoretically you might want to have different attention heads with different functions. But in standard models nowadays, what we use instead is we have multiple attention heads, but we just let the attention heads kind of learn on their own what they would like to focus on. And here's an example of basically this word making attending to other words in the same sentence in self-attention, which I'm going to talk about in a second. And you can see that making, one of the attention heads is attending to making itself. There are other attention heads like the blue attention head, orange one, green, red, which are attending to more difficult, which is kind of the object of making. And then you have another attention head that's pulling in information from like the previous word to making. So you can see that each of these heads has kind of specialized in a different like form or like function that it should be achieving. So that's good because, you know, there are things like local context, like, you know, the previous word 2009, which could be very useful, but there's also other varieties of context farther away, like the object of a verb that could be important for making particular decisions as well. So another common improvement to attention is supervised training. And normally we just train the attention together with the entire model. And however, sometimes we can get like quote unquote gold standard alignments a priori. And gold standard alignments are basically, could be manual alignments where we've asked a human annotator to say specifically which words in the source correspond to which words in the target. And the reason why we might want to do this is because, as you can see here, or no, as you can see here, even though this is a relatively good example, it's not always the case that attention will focus directly on the words that are being translated. Like, for example, here, the period only has a very vague attention on the period in the input. So because of this, you can't necessarily like look at the attention value and immediately tell which words are being translated. And that's even worse in the case of something like multi-headed attention. However, like as I talked about last class, you know, if you're a human translator using machine translation, it might be very important or useful to you to know which words were translated into which other words so you could check that they're correct, or something else like this. And in that case, doing supervised training with manual alignments or something could make sure that at least, you know, some of the attention heads correspond with human intuition about which words were translated into which other words. Another way you can get gold standard alignments is by using a strong alignment model. So you might have an alignment model that was trained on manual alignments or something like this. And you could also use that to kind of bootstrap the training of your model. And this can also improve accuracy overall by making sure that the model is attending to like words that are actually aligned as well. So exactly how you do the supervised training, basically you can do a number of things, but the simplest one is you just have another loss function that you incorporate into your model, where the loss is higher if the alignments are like incongruent with the annotated alignments. And so you can do things like take the norm, the L2 norm of the difference between the alignment vectors or something like that. Okay, and now I'm going to go into self-attention, which is very widely used in NLP nowadays. And self-attention, basically the idea is, up until now, we talked about things like recurrent neural networks as a way to gather encodings for each word in the sentence. But another way you can do this is you can have some sort of attention that uses, that where you attend each token in the sentence that you're looking at now attends to the same sentence itself. So for example, the word this would attend to this is an example. The word is would also attend to this is an example, et cetera, et cetera. And the basic idea here is that this function is kind of a drop-in replacement for another type of word level encoder like RNNs. And to calculate the representation of each word. So for example, for this, the word this might attend to this a lot, is a little bit, and the other one's not very much. Is might attend to is and its subject and object and other things like this. The motivation for this becomes very obvious if you think about the translation of words like the word is, or maybe the word run is a better example. So the word run, depending on whether you're running a marathon or running a company or running along the road or running along a creek or something like this, run might be translated differently. So if the encoding for the word run pulled in the subject information about the subject and the object, that would make it a lot easier to perform like lexical selection in translation or something like that. So why would you want to use self-attention instead of an RNN or something like this? Unlike RNNs, it's very parallelizable, which allows for fast training on GPUs. You can calculate all of the words in the sentence at the same time. So this is probably the most important reason why people like using transformers, like using self-attention and the transformers that I'm going to be talking about in a second. Another reason why people like it is, unlike both RNNs and other options like convolutional neural networks, it can easily capture global context from the entire sentence. So you'll note that every time each word is attending to all other words in the sentence. So that gives a very direct connection to, pulling context there. In general, transformers seem to yield pretty high accuracy on a large number of NLP tasks, although it's not 100% clear that they're actually all that much better with respect to accuracy. Like there's this study by Chen et al. That compared them with RNNs, and the results were similar essentially. But the advantages here of like fast training and being able to easily pull in global context are widely appreciated. One downside to this is quadratic computation time. So essentially, because like you can even see this computation time directly from this attention graph here. So you can see that if the length is 4, you have 4 times 4, 16 attention values here. And this can become onerous if you're using very long sequences to compute. So there's also a lot of different methods to improve over this recently. So now that I've introduced a bunch of improvements or kind of elements that go into attentional models, I'd like to introduce the transformer, which is kind of the core element that is used in most state-of-the-art MT or NLP models nowadays. And basically, this is a model that uses both self-attention and regular attention between the source and the target. So we have a transformer encoder and a transformer decoder, where the transformer encoder takes in some word embeddings. It adds something called the positional encoding, where the positional encoding basically is another word embedding that tells you not the identity of the word, but rather the position of the word in the sentence. So instead of saying, like, this is the word summary, it would say this is the first word in the sentence. So you add them together and you get like summary and first word in embedding, indicating that. Then you run this through multi-head self-attention. You add in the original input and you do something called layer normalization, which basically kind of normalizes the outputs to be average of around 0 and norm of around 1. And then you run through a feed forward network, and then you do the addition and normalization, and then you do this over and over again, 6 times or 8 times or 10 times or whatever. And then on the right side over here, you have the transformer decoder, which is very similar: output embeddings, positional encodings, self-attention. But you also have additional cross attention that attends to the input here. So that's kind of the place where you get the attention that I showed before between the source and the target here. So that this is in the cross attention part. And then in the self-attention part, you have the encoding of the sentences like you have here. So you're doing both in the transformer decoder. So often we talk about like the transformer as kind of like a monolithic block that is used in translation models. But actually, it contains a lot of the tricks that I talked about before. So it contains self-attention, multi-headed attention. It's using normalized dot product, or actually maybe bilinear attention would be more accurate because it's multiplying by a weight matrix for the key and the queries. And it has positional encodings. It also uses a whole bunch of training tricks, such as layer normalization, helping ensure that layers remain in a reasonable range. It also has a specialized training schedule where you have the atom optimizer, but you have a specialized learning rate that kind of gradually ramps up and then slows down. In the transformer paper, they also used a technique called label smoothing. I'm not going to go into a lot of detail about this, but basically it kind of smooths out the distribution you're predicting. So you're not predicting 100% probability on the true next word, but you're giving a little bit of probability to all of the other words. This is pretty effective in a wide variety of neural network-based tasks. And you also have a masking method for efficient training. And so the way this masking works is basically you decide when you're calculating the representation for a particular word, you decide which context to attend to. So when you're calculating the representation for the word I, you only attend to the context in the input. When you're calculating the representation for the word hate, you attend to any of these things over here. And similarly, throughout the entire calculation of the representations for the decoders. So on the encoder side, you always attend to all of the other words, but on the decoder side, you only attend to words in the input and previous words in the output. And so this was about transformers. Taking a step back, we can kind of take a unified view of the models that we've talked about so far in this class. So we have sequence labeling, where sequence labeling has a feature extractor. And then given the feature extractor, we have a feature for each word and calculate the output. So this is what everybody is doing for assignment 1. And then we have sequence modeling, where we have a feature extractor. So these can actually be exactly the same thing, and calculate one representation for each word. And then we have essentially a masked feature extractor here, where we calculate representations that can reference any of the things from the input feature extractor, but only things that occurred previously in the current output sentence. And then we predict the words here as well. Cool. So this is all I have in terms of the lecture content. And then I'm going to try to go through the code for the transformer just a little bit. And then Patrick's going to introduce what you need to do for the assignment. Are there any questions about the lecture content that I talked about here? Okay, I guess not at the moment. So if you know about this already, this might be a bit of review. If you're not familiar with this, it's very important. So please do ask questions, go to office hours, other things like this. And then the final thing I'd like to do is go through a brief code walk through this thing called the Annotated Transformer. And this is a very good thing. It's linked on the class site. And basically what it does is it demonstrates how you would actually implement the transformer model together with all of the description from the original paper. And so basically, if you look at the model architecture first, the way it looks is we're talking about an encoder-decoder architecture. We have our encoder here. We have our decoder here. And sorry, my computer is very slow nowadays because my battery is broken, as you heard last time, but I'll try to do this nonetheless. We have our source embedders. We have our target embedders, and then we have some sort of generation policy. So this would be, like something that helps us do sampling or helps us predict the probability of the next token. And we take in and process source and target sentences. The encoder encodes the source sentence, and then the decoder encodes the target sentence and the memory. So I believe this is the encoded source sentence. And then we have the source mask and the target mask. And the generator is basically just doing a softmax like you're all familiar with. And so this is the kind of encoder architecture. This is the decoder architecture. And then we have our generator here. And one other feature of the transformer is basically we have n times this this encoder block and decoder block. So this method here produces n identical layers. So it copies each module, so you get n of them. So that allows you to do the nx here. The core encoder is a stack of n layers, where we also have layer norm after all of them. Or no, sorry, this is a final layer norm, I guess. And then we pass the input and mask through each layer in turn. So we just have a for loop over each of the layers here. And the layer norm, what this does is this basically attempts to normalize. So I mentioned we're trying to set the mean close to 0 and the variance close to 1. So you can see that that's kind of doing that here. And we add dropout. Oh yes, so dropout is kind of like regularizing the model to prevent it from overfitting. We have layer norm. And then for each of these blocks, you'll notice that we have the multi-head attention, and then we have this add-in norm after this. So this sublayer, what it's doing is it is doing layer normalization. And it's doing layer normalization. It's calling the sublayer function here. It's doing dropout over the output, and then it's adding a residual connection. So that's kind of the yellow block in the transformer stack here. And then each layer has, in the encoder, has 2 sublayers. One is the self-attention layer. One is the feed-forward layer. And then this is cloned, you know, 2 times essentially there. Then the decoder also has a stack of n layers, basically. And the decoder is the same, except in addition to having self-attention, it has source attention in the feed-forward layer. So that's basically what you can see here in the diagram. And then it talks a little bit about masking here. So that was the masking that I talked about in the lecture, where you're basically creating this mask that gets rid of all of the things that are in the future for the decoder. And this is applied only to the decoder, Then finally, I'm going to talk about the attention, how the attention is done within the transformer. So basically, the transformer attention is doing this sort of dot product attention with scaling. You take the softmax and you multiply this by the value vector. So that's, you know, what I talked about in class. And that's all implemented here. It's basically doing a matrix multiplication between the query and the key vector here, query and key matrix here. It's taking the square root based on the size of the query vector. Actually, this is dk, but this is query, so that's a little bit strange, but you know, it makes no difference, as I mentioned before. And then you take the softmax and you multiply the attention by the value vector. So that's basically the multiplication here. So you can see, you can make a map between the equations of the code. And then there's also implementation of multi-head attention. This is a little bit more involved about exactly how this is implemented. So I'm not going to go through all the equations here because I want to leave time for Patrick. But if you want to look at exactly how the multi-head is implemented, you can see this here. And yeah, that's the basic idea of what this looks like. I think it's important to know what's going on in these models, but if you want to like actually use this in your code itself, it's also PyTorch is also nice enough to just have this transformer class for you that you don't need to implement yourself. And basically, if you look at this, it's doing the same implementation that I just showed you, but it's, you know, maybe more optimized, or it's right, so you won't be making mistakes. So if you're actually going to be using this, I suggest just using the transformer module, but I think it's important to know what's going on inside so you can understand the behavior and other things like that. Great. So that's all I have here. Are there any questions about the implementation or other things?
I have a quick question.
Yes.
Isn't the annotated transformer, I seem to remember, like, it's slower because it uses for loops for the batches instead of converting them into like multi-dimensional tensors. Mm-hmm. Is that ringing a bell, and is that accurate, or?
Let me, I didn't cover batches. So like batching is important. It's a very, important thing, because like basically when you batch together multiple sentences, you can get them to like all process in a single GPU call instead of in many different GPU calls. I talked about this a little bit more in advanced NLP. I don't see.
I actually think I was thinking of the multiple heads, the attention heads. Because I think it actually batches by input sequence length.
It definitely batches because he has access to a mask. So if he has a mask, it's definitely batching. Yeah.
Yeah, I don't
Otherwise-
like. I seem to remember this was actually implemented pretty well, pretty efficiently. I don't. I didn't actually talk about how the multi-headed attention is implemented, but it's implemented in a clever way, which also makes it hard to read, which is why I didn't go into the details quite as much here.
Okay.
But I do think this is actually a pretty good example of how you would implement it efficiently as well. Although I'd have to go through in more detail to make sure for sure, but that's a good question. What I can tell you is the PyTorch one is definitely implemented efficiently. So if you want to look and see the best way to do that, you can look there. I'll turn this over to Patrick then, who will, I guess, go through the assignment for assignment 2. And this is now available on the website also if you want to follow along.
Let me share the screen. Okay, do you guys see the right screen? Yeah, cool. Yeah, so I'm going to introduce assignment 2, which was released today. The code still needs to be uploaded, but all the instructions are there. Yeah, so let's get started because we're short on time. So, and this was developed by me and Vijay, which will explain the later part of the assignment. Cool. So the task for this assignment is machine translation. So as Graham described, given a source language sentence, you want to relate to a target language, so conditional language modeling. And the goals of this assignment are to understand how the standard data processing pipeline is used in MT, to be able to train MT models, both bilingual and multilingual, using an MT framework, to learn how these models are evaluated, and finally to investigate methods to tackle the data scarcity problem in low resource language pairs, which is what you're going to tackle in this assignment. So for requirements, you definitely need a machine with GPU. Unlike the previous assignment, it will be very, very hard to run this on a CPU, as in it will run but not in feasible amounts of time. I didn't test it, but I'm pretty sure you can run it on a call-out. But still, if you have access to the credits, I would probably recommend doing AWS for this. And in terms of packages, it's mostly the same as the last assignment. You can almost certainly reuse the environment that you have. We tested it. And this assignment will also use FairSec as a backbone for training models. So FairSec is like a sequence modeling toolkit, and it automates data loading, training, decoding, and a bunch of other small, not boring, but like you might not want to consider for this assignment. And it also supports many other tasks other than translation. For the basic requirements, you will not need to dive deep into FairSec, but if you want to modify for the actual requirements, you probably will need to dive into FairSec. And yeah, you also need to install Sacreblue and Comet to evaluate your models. But this is all automated in the instructions of the assignment. You just have to follow the assignment and everything should be installed automatically. So the assignment is a collection of scripts which will pre-process your data, train your data, and score your data. We'll go over them in a few slides. So for data, you'll be using the TED Talks corpus, which contains parallel data between English and 58 languages. And you'll focus on 2 low resource language pairs, English Azerbaijani and English Belarusian. So to pre-process the data, there's a script that does the following steps. It will read the raw parallel data. It will learn about byte pair encodings separately for the source and target languages. And in particular, this assignment will use sentence piece, which is a particular implementation of byte pair encoding. We'll apply BP to all splits. There's also a very minor data cleaning pipeline, which just filters based on the size of the sentences. And finally, you'll binarize the data, which makes it efficient for FairSec to train. And crucially for this assignment, we simplified a bit. Sometimes you also do some tokenization using Moses prior to learning the BPE, but in this case, we simplified and we just use sentence piece, which works fine by itself. But sometimes people do Moses tokenization before, just as a remark. For modeling and training and generation, we'll use the transformer architecture as described by Graham. Embeddings will be shared between source and target, despite the fact that they use different BPs, this is still possible. And this will be trained to minimize cross entropy with Adam, and decoding will be done using beam search. In particular, it's fixed to beam search of 5. And this is an example of what the scripts call, and it's just like CLI for Farsec, so you don't have to worry about too much about training loops or anything. For evaluation, for MT, you traditionally don't look at perplexity because it's not a good measure of how the models perform in terms of translation. And in this assignment, we'll use two metrics: BLA, which is the de facto standard for MT evaluation, which uses n-gram overlap between the reference and the target. And because there's some concerns with the reliability of BLUE and its correlation with human judgment, we'd also consider COMET, which is part of a new generation of neural model-based metrics, which rely on pre-trained models and are trained to optimize directly human correlations. Again, you don't have to think too much about it because there's a script that already does it. It's just good to know that you'll evaluate the models based on both. Okay,
Yeah,
I'll turn it over to Vijay.
Thanks, Patrick. So the minimum requirements for this assignment involve first training these MT models on bilingual data. And so here we expect you to train models from Azerbaijani to English and vice versa, and also Belarusian to English and vice versa. Next slide. But then the more interesting bit, which is also required in the minimal our minimal expectations, is to train multilingually using a transfer language, which in the case of Azerbaijani is Turkish. And we have scripts to do this already for both bilingual and multilingual, but you'll have to modify these scripts minimally in order to support Belarusian. We've also introduced, because nowadays, while multilingual training is still very effective, there's a new paradigm that's become super popular, which is fine-tuning a massive multilingual model that's been trained on a large amount of data, and to allow you to try this approach, which is now pretty predominant. You can also, instead of doing multilingual training, you can fine-tune a model that we have provided that has been trained on the Flores 101 dataset, which is like a massively multilingual MT dataset. And you can instead use this strategy, and this will also get you to the B plus grading range. Next slide. But I think where this assignment gets really exciting, and what you need to do to get an A-, AR, A+, is to add extensions beyond what we provided in these scripts. And I think Graham will be talking about a lot of this in the next week. Some of it he already talked about this week, but data augmentation, which he hasn't talked about yet, is one very promising strategy. You could use these terms will make more sense once his lecture is completed. Next slide. You can also try to use better transfer languages. We've currently suggested 2 basic transfer languages for both Azerbaijani and Belarusian. But as you might remember from the lecture last week, there's more of a structured way you can choose a good transfer language based on your knowledge of typology or based on learned models. And we encourage you to try this and see what results you can get. And then lastly, in terms of the data, our baseline models use sentence piece for byte pair encoding, which is basically a way of breaking up words into subwords. But there's like many other ways to do this. And this is a particularly interesting and active area of research. And so we encourage you to consider different variants of this. And lastly, this is probably the most broad category. Feel free to try different models, different training algorithms, different ways of doing learning, or different, there's like a huge space here. So we really encourage you to be creative, and also when you choose something, analyze it and try to deepen your understanding of why these things work in machine translation.
And just for reference, like the assignment includes a bunch of references to different techniques that seem to work for this. Feel free to follow them or do your own literature review, of course.
And in terms of what we ask from you when you submit the homework, first, you need to submit the code, which should include both the minimum requirements for like the scripts that you've modified in order to support the bilingual and multilingual training for the language pairs in the assignment, but also for the additional modifications that you make. We also, and this is probably the most important part, we want to see a write-up that provides some solid analysis of of the methods described in the assignment. And lastly, we don't want you to submit the actual model files because these are quite very large and it'll take a long time to upload. But we do want to see you submit your model outputs. Once you start playing with the software, it'll make sense what this is. But basically, this way we can compare the translations that your model predicts with our references and reproduce your evaluations, just to make sure everyone's on the same page. And these are all submitted on Canvas as a tarball, like the previous assignment. And so I've been touching on this, but the grading tranches are like, first, for the minimal requirements, you just need to reproduce the, modify the scripts that we have for both Azerbaijani and Belarusian, and that'll get you a B. If you couple this with detailed analysis, then you'll get a B+. To get an A-, you need to implement at least one pre-existing method or a new method to try to improve the ability to do this multilingual machine translation. Next slide. And then to get an A, we expect you to do two or more several methods to improve multilingual transfer. And you might find that some of these methods are more lightweight than others. So it might be quite doable to try several. And we also would hope that one of the methods you try is actually novel, something that you've come up with. And then lastly, building on that A, if you've done something that is particularly extensive or creative, or your analysis is like super compelling, then that will get you an A+.
And just to recall, this is a group assignment, unlike the first assignment. So it's expected that it will be done in groups of 2 or 3. I'm not exactly sure how this will be arranged, but I'm pretty sure Graham and the others know what's the best way to do this. But just to clarify expectations.
Yeah, regarding groups, feel free to make groups. Obviously you've already talked to people about the language in 10 things, so that would be one option, but you're obviously not obligated to do that. If you don't have a group yet, but would like to form one, please, I think one good idea would be to email the TA mailing list or put a post on Piazza by around the time the first assignment is due, which is very soon, obviously. And so then, like, when you finish the first assignment, if there's anybody who doesn't have a group yet, we can try to match you up with somebody else. So yeah, are there any questions about these?
Yeah, just as a final, if you need anything, feel free to come to our office hours, but mine and Vijay's or the other TAs can potentially help you as well. And if you want to contact us, Piazza, obviously, or feel free to email us or the TA mailing list.